Yeah.
Good evening, everybody. A very warm welcome to all of you. I'm Saurabh Kumar, in charge of community for H2O.ai. Tonight we have with ourselves Mr. S.K. Reddy, who's going to be talking about magic of text summarizations using deep networks. And just as a side note, you got a ticket when you entered and signed in. Keep that ticket with you. There's going to be a draw at the end of the event. And sorry. Yeah. So with that ticket, you guys stand a chance to win a ticket to H2O World 2017, and the textbook that's right on the table. Over to Mr. S.K. Reddy. Thank you.
I'm not sure I need this, but I can talk loudly. Can you guys hear me in the back? Okay, wonderful. Cool. Can you turn this off, SK? By the way, his name is SK and I'm SK too. SK.
Different full forms.
Yeah. Good evening, everyone. Thank you very much for coming. Before I start presentation, I know it's all exciting title there, but I'll talk about summarization and neural networks and stuff. I want to tell you a story. Okay, so can you hear me now?
Yep.
Okay. I'll hold it here and hopefully I think you can hear me well. Otherwise I'll put it here. Before I start the presentation on the magic and the summarization and the neural networks and NLP, all of the stuff, I want to tell you a story. After I started learning NLP, especially on the summarization and also language translation, I realized I made a mistake when I was in my 7th grade. In my 7th grade, in my language subject, I was supposed to do a translation and also summarization. There was a word called Great War. It was actually talking about a war. I never realized that the name Great War should not be translated into a different language. As the meaning of the word great, it has to be just Great War. That is the one lesson I think I've learned in the translation and summarization part. But we'll talk about the actual summarization and translation. Being an Indian, I tend to talk very fast, and if you feel I'm talking very fast, please let me know. I will slow down and then repeat whatever I said. NLP is one of that part of AI which is really getting prominence and importance. And the best part is the best papers, technical papers published in NLP research are just in 2015 and 2016. So the techniques, the approaches, solutions being proposed in NLP, text processing, etc., are very recent. And I'll talk about some of the papers. All my solutions are from technical papers published, and maybe there are some frameworks already available, open source tools which you can start programming, and I'll talk about that also. Let's talk about summarization. Typically, summarization is you have a huge amount of text and you have to summarize that. Those are some of the examples of the original text and the summary part published by Google guys. For any type of NLP solution, whether it's a translation or summarization or any such activity, the basic building blocks that's being used are very similar. I'm going to talk about those building blocks. At the end of the presentation today, I'm confident that you will be able to go back home and start programming on these activities. And the best part is, programming summarization solutions or translation solutions or anything in NLP is extremely easy because there are so many frameworks available that maybe I think a couple of lines you can program. I was doing a tech workshop a couple of weeks ago in Big Data Conference. I was showing to do a sentiment analysis of around 9,000 tweets. It takes only 20 to 23 lines of code. So in other words, I think coming out with an NLP solution is very easy, except that you got to understand the concepts behind this, what's happening in the model very clearly so that you can actually call the right APIs. And I'm going to talk about that. at the end of this slide, I would have done half my summarization presentation. You would have actually got all the 50% of the summarization. These are some of the building blocks I would like to talk about. In machine learning, computers can do 2 plus 2 easily. But how do you make computers process text? You got to convert the text into some numbers, which is predominantly called as vectors. There are many tools available, but there are different approaches being used to translate words into numbers. I'll give you a couple of examples. I didn't want to have too many slides because I have 23 slides, hour to talk, so I didn't want to have too many slides. One of the simplest approach of converting text into numbers is called one-hot vectors. If you have, let's say...
Are you going to share the slides?
Yes. I'm also recording it, so I'm going to actually put it on YouTube too eventually. That's why I'm recording myself, just to make sure one-hot vectors are nothing else but, if you have a collection of your vocab, typical experiments in NLP, let's say Stanford or Oxford, even when they publish NLP solutions, the typical vocab size is around 50,000 words to 80,000 words. Anything more than that, it's becoming too computationally expensive. You can actually theoretically have 1 million words vocab, but typically, right now I think 50 to 80,000. So let's say you have a vocab of 50,000, and if you arrange all these words in a sequence, the first word, the one-hot vector for the first word will be 50,000 zeros, but the first zero will be replaced by a 1. Pick a fifth word in the vocab. The one-hot vector for that fifth word in the vocab will be 50,000 zeros, except the fifth zero is replaced by a 1. It's called one-hot vector. That's the way you convert vocab into or text into numbers. That's one way of doing it. There are many solutions which work very well with one-hot vector. Actually, I have a solution which I've developed and posted on I think GitHub and also on my LinkedIn, where there's a section in NLP called question answering. You can ask questions to the computer. And this is different from the pattern matching where you search for the pattern and find the answer, but this is different. Let me give you an example of question answering. Sally went to the kitchen, John went there too, it was bright morning, and Sally said a hi too. And if you ask the computer, who did Sally say hi to? In our language model, I think as regular human beings, we know she's saying hi to John. But the computer doesn't know that John is in the kitchen, because in the story I never said John is in the kitchen. Sally went to the kitchen, John went there. Computers have to comprehend text and answer questions. One-hot vectors was the approach I took for that solution, and the accuracy rate was 72%, which was the same when Stanford published, I think, a year and a half ago, 2016, they published a paper where their accuracy rate was over 72% on question answering and text. So one-hot vectors will work in some instances or many instances. There are another way of translating words into vectors, and that's called co-occurrence vectors. Now, co-occurrence metrics or vectors are not that popular, but it's a very good exercise if you guys want to understand how text is converted into numbers. It will be a good exercise. The summary, the way you explain co-occurrence metrics is you identify the number of times a word occurs next to, that is before or after the other two words, and then capture the frequency. And when you capture the frequency of all the words compared to all other words in your vocab and put that in a table, either the column or the row becomes the vector for that specific word. It's called co-occurrence. Both in one-hot vector method or in co-occurrence vector method of converting words into vectors, the sequence of the word, the message or the essence, the information of the sequence of the word is lost. For example, the cat sat on mat gives you a certain message, but the mat sat on cat doesn't make any sense. But for one-hot vector method or co-occurrence metrics, it doesn't matter, it will be the same vector. for the words. So in some instances, when you do summarization or when you do question answering, when you do any other type of analysis, you may want to pick the right vector. And there's no one single solution on what's the right conversion of words into vector. There's something called word to vec is another solution available already. It's a couple of lines of code you can call. And also GLOVE is another method. Global vectors, GLOVE, is another method of calling vectors. But what am I trying to communicate in the word embeddings? The best part is when you convert words into vectors, they capture the essence of where they occur in a sentence or in a paragraph. And that you can see when you project these vectors onto a two-dimensional image. This is a two-dimensional plot, TSNE they call it, of all the vectors of words you have converted from your vocab. Every time when you define a problem statement, let's say you're developing a solution for a healthcare situation, or let's say you're working on a solution for a retail company, or if you're working for your company, which is a product-based high-tech company, you have your own vocab. Talking about vocab, let me tell you a story which I've learned recently. English language, how many words are there in English language? The common language we all speak. 5,000, okay? 10,000 someone said, okay? 20,000? 50,000, okay. 500,000. Typically it's around 500,000 words are being used. But here is the best part. Do you know how many words are used in medical domain? English words, not the Latin derivatives or the Greek derivatives or whatever derivatives. I'm talking about the regular English words being used, which have meaning. Sorry? Much more? Smaller. Smaller, okay. So less than 500,000, okay. Any other guess? Don't worry, I'm going to tax you for that. 1,000? It's 3 million. 3 million words are used in, there are so many words, of course, which talk about various body ailments and treatments and whatever lab tests you go for. There's so many words people are using. Now, you could have a debate on, are they words or names? Now, whether it's a name or a word, every such word actually has a message or a meaning in it. When you say pulmonary cardio disorder, PCD, even though it sounds like a name, it actually has a meaning because the patient understands something, the doctor understands, the technician, the radiologist, they all understand the same way what it means and could be slightly different with respect to their jobs, what they're doing. Anyway, so that's about word embeddings. When you translate words into vectors, and if you use the word to vec method and GLOVE method, they actually capture the essence. And if you see the words here, of course you can't see it here. When I post the slides, you can have a look at that. Or if you give a Google search on word embeddings, you'll find lots and lots of images. You will see words of similar nature which co-occur more frequently. They appear on that two-dimensional picture closer to each other. Like the names of the countries, names of the capitals of these countries, names of currencies. They occur close to each other. Someone did, and yes.
What are the X and Y axes?
The X and Y axis is not actually a dimension. See, when you project a bunch of words into vectors, they are multi-dimensional. They could be hundreds of dimensions. It could be 100 or 300 dimensions or 1,000 dimensions. Now, when you actually are looking at a two-dimensional image, but you actually cut through the 200-dimension picture, which is actually hanging in the space, you cut it, and you just see where they hang close enough to you. So there's no actually X and Y dimensions here, but that's one view of the 200-dimension or a 500-dimension globe, or it's not really a globe. I think it's just a massive amount of data hanging in the sky, and that's what you see.
If you've done PCA for visualization, PSN is just a better rating.
Yeah. PCS I think was earlier done. I think TSNE I think nowadays is more commonly used, and there are a bunch of programming solutions available already to do a TSNE. I was quite fascinated with this. Someone actually went ahead and said, okay, instead of word vectors, people actually went ahead and started creating sentence vectors, then paragraph vectors, someone went ahead and created an article vector on Wikipedia. So 3 million articles on Wikipedia, each article gets one vector number, and when you post those and you have a TSD image of that, you can see the articles which are similar, they're all clubbing together. All the articles about films or about science and albums and all of these things, they've naturally come close to each other. So in other words, I think when you guys read about word embeddings, the message you want to take with you is, it's another way of converting word into numbers, and also I think they capture an essence of what are the similar words that come close to each other. Next building block is the most important one, and a little complicated one, is there's something called recurrent neural networks, which actually reads a sequence of inputs, remembers that the inputs, and use that information for whatever processing you want it to do. Let's say if you want the recurrent neural network to do a translation from, let's say, English to French, you give a series of words in English in a sentence, it remembers all those words, and what it remembers, that you can get into the details, but it remembers all the words, and then based on the training you've given to the model, it translates that into a different language, or helps you in answering the questions, or helps you in summarization, all of these things. But that's the recurrent neural network. But one problem scientists found in the last year and a half is when you have long sequences, recurrent neural networks actually were getting into a problem. It's called exploding gradients or diminishing gradients, where if the input is long enough, it starts forgetting. In simple human language, let's say, it starts forgetting what it read 20 words, 50 words, 100 words ago. So they came out with a new one. And also, I think if you are a smart research, you've got to come out with something on your name so that people eventually can use it. So this actually theoretically was proposed, I think, around 10 years ago in 2010, but I think got prominence only in the last few years, a couple of years maybe. It's called long short-term memory. This is a variation of recurrent neural network. This has 4 layers of transactions that happen inside it. I'm actually trying to explain it in a very layman's term. There's lots of mathematical equations there. I can even explain those mathematical equations, but for the context of 1 hour summarization presentation, I can't get into the details, but LSTM takes a sequence of words, also remembers, but it remembers those words more efficiently. It won't forget as much as RNN used to do. So there are multiple gates in it. There are actually 3 gates: forget gate, input gate, output gate. So the reason why it remembers it, if certain words are no more required for the model to remember, the forget gate actually triggers the model LSTM to forget that part of the information. So it starts adjusting itself to what's relevant, what's not relevant. And that's part of the magic. If you really want to understand what's happening inside, it's a huge matrix, and there's lots of multiplications of numbers happening, but miraculously, that's why I use the word magic all the time in NLP, because sometimes I'm not able to explain it, even to myself. So I can't explain it to you guys too, why certain things are happening, but I think those things happen. And of course, there's lots of blogs written. If you guys want to read that, we can find out. But LSTM is the most prominent variation of RNN that's being used. There's another variation called GRU, Gated Recurrent Unit. One of the papers I'm going to talk about actually have done the experiment on both GRUs and LSTMs. They found the accuracy rates and the response rates of LSTMs is better, and hence they actually encourage people to use LSTMs. But GRUs are also another variations. And one of the differences between LSTM and GRU is GRU has less gates than LSTM. So it says, I just want you guys to know this is LSTM repeated 3 times. LSTM is just one single sort of a box which is actually taking the information at any timestamp t, and then timestamp t+1, you give a new input, and it's actually updating its hidden state. So the output, the only one output which you need to constantly keep in mind for an LSTM is it's something called hidden state. So whatever it's remembering, the information it's remembering is encapsulated in this vector called hidden state, and that's what I think you want to be using to process. Let's say you want to do a translation from one source language to English to French. You give an English sentence and it remembers and memorizes and updates its hidden statement. At the end of the sentence, and if you say, okay, now it's your turn to translate that into French, it starts translating into French using hidden statement.
Are there any particular model for stop words that you're using for filler words? Is that part of recursorization, or are they excluded as some part of priority process?
You got to input all the words in a sequence. For certain solutions in question answering and some translations, I've seen people eliminating stop words, but in such a sequence where you are trying to do translation and summarization, you got to have all the words. Let's say the cat sat on the mat, so you don't eliminate the these and ons and stuff. You have to put all that, because then it knows. In translation, for example, it has to understand the gender, and summarization too. If you give them a couple of names of people, what they have done, and then you keep on explaining, and in summarization, instead of repeating the names multiple times, the model has to know John and Sally, and John is a male and Sally is a female, and it understands who's a male and who's a female, and that's being used in the summarization part. So to answer your question, no, you don't eliminate the stop words when you're doing the. Okay, so now let's go to the next building block, which is the most frequently talked about. Of course, this is no more used, but this is definitely, I think, you need to understand. So if you use an LSTM, you input a sequence of words in, and then when you're done inputting the sequence, you want the model to do the summarization. So it takes the inputs in a sequence and gives an output in a sequence. It's called sequence to sequence model. Brilliant way of naming it, but sequence to sequence model, which actually takes a sequence in and gives a sequence out. And this is used for any type of NLP activity. The question answering, translation, summarization, even though we're talking about summarization today, but this sequence to sequence would be the first stepping stone for you guys to actually do to the processing. Now, I know I always try to explain the concepts in machine learning or artificial intelligence without using mathematics, but you can't get away with the mathematics. You've got to be familiar with the mathematics. So also on a side note, if you want to learn an NLP or even ML or even image processing and audio processing and stuff, there are only two sources of information online. You can just go read lots of technical papers, and you can read maybe some blogs, and there are not even books available too. I think like technology has not come to the stage where you can actually have. There are a couple of books, but not really, not the best books I would want to. But the problem with the technical papers is they are not written with an intention to teach you. They are written with an intention to show how smart the author was or is. So you will find lots and lots of these mathematical equations in all of the papers. You just can't. But it's like the bitter pill. You got to start understanding. So I'll try to explain this mathematics in the next slide too. The way you read this is the probability of the outputs, which are shown as y1, y2, y3 to yt prime, based on the inputs x1, x2, x3 till xt, is same as the product of probability of each word given the previous word it has outputted, that is y1, y2, y3. Let's say you are actually talking about the probability of fourth word. The probability of fourth word depends on the probability of the first word, second word, third word of the output, and something called, there are different words used, but let's talk about hidden state. The hidden state of the LSTM and the previous outputs together, once these are given, it's easy to find the probability of the current word. So at timestamp t, if you want to find out what the word is, you've got to know what the hidden state was of the LSTM when you started, when you're done with giving the inputs, and then what are the words you have outputted till now. That's how you read this. Anything else? Yeah, hidden state. The last hidden state, V is the last hidden state of the LSTM. So let's talk about more exciting mathematical equations. The next one.
Question. So the condition with respect to x1 to xt is not appearing on the right side. So is it being summarized in V?
Okay. So when the model takes these as inputs, what it's doing is it's actually updating its hidden state. So you're actually taking the hidden state. So all the x1 to xt, you've done the inputs, and that's actually encapsulated in your hidden state. So you're actually using the x1 to xt there in that. So we talked about a single LSTM block, and then we use the same over a sequence of events coming in. But then some people said, you know what, this is too complicated for software engineers. I'm guessing all of you are software engineers. So we want to break it down into two different pieces. So they said from here to here, end of sentence token, this we are going to call a different name. And from here to end of state token, end of sentence token, we're going to call a different name, even though it's exactly the same LSTM. And that's called encoder and decoder. But conceptually, it's exactly the same. You have an encoder and a decoder put together. You give inputs to the encoder, and the word encoder means it's actually encoding stuff. And decoder is decoding the stuff. That's it. But someone wrote a paper on that, and there's a lot of mathematical equations for that. You'll be forced to read those papers, but that's part of the game. So I'll explain again the same. The hidden state, ht at any timestamp of the encoder, is dependent on all the inputs until that time and the previous hidden state. So every time you give an input, it assimilates that input and updates its hidden state until you're done. And all the hidden states you compute over a period of time when you're doing the inputs. You create something called an output vector or a context vector, which is actually a function of all the hidden states. You need to remember all these hidden states. If you're a programmer, you know that. I think because the model is outputting hidden states, you can store it in some place and use them later. So a context vector is created as some sort of a function. Now this is the function you can decide, some sort of a nonlinearity, which you can take. There are a bunch of nonlinear functions available. But for now, let's say you have a hidden state at any point of time, and all the hidden states are put together. You create a context vector. That's the job of an encoder. And decoder, it uses that output vector, and as I mentioned to you, yt, the output at any point of time t is dependent on all the outputs till that time, and the context vector is also can be shown as a different nonlinear function, which is dependent on the previous output and the hidden state of the decoder and the context vector. So let me explain again. Encoder has a hidden state and a decoder has a hidden state. When you give all the inputs to the encoder, the last hidden state will capture the complete essence of all the inputs you have given. So you take the last hidden state of the encoder and then give it to the decoder, and decoder starts outputting, but in that process, it's also updating its own hidden state. So you need to keep track of what is the current hidden state of the decoder and the hidden state, the last hidden state of the encoder, plus the output in the previous time step. Are the three numbers typically you keep track when you go to output in a sequence. Let's say doing a translation, language translation, or a summarization. When the output starts, the first when the word, and typically it could be a token, special token you give, the end of sentence token for the decoder would act as a trigger for the end of sentence token for the encoder will act as a trigger for the decoder to start doing its job. That's an encoder decoder function. Recording is not. In the decoder, if you look into the probability of the current word yt is dependent on this static number which is the last hidden state or the hidden state computer, the output vector computed based on all the hidden states of the encoder, which is actually a static number, it's not changing all the time. But let's say when you do a translation, let's talk about summarization. How does a typical human being does the summarization? You read, let's say 10 lines. Let's say summarization is used for giving a headline to a news item. If you are a news agency and if you write a big article and now you want to give a nice title or headline, you can ask your summarization tool and it will give you a bunch of suggestions of what could be the nice headlines. For creating the summary statement, it's using a constant, which is actually a static output vector, which was given by the encoder. But human beings, when you're doing a translation, let's say halfway through the sentence, you want to go back and say, what was the fifth sentence that was there? Let me read that information again. Or when I'm trying to output the second sentence in the summary, I want to focus only on the fifth, sixth, and seventh sentences of the input. So I want to actually pay special attention to certain portions of your input when I'm doing my output. Make sense? There is a mathematical concept for that. It's called attention. So you train the model in such a way that instead of taking a static output vector C, every time you output, the decoder outputs a word YT, instead of just depending or based only on a static number called C, go back and check on those hidden states at that specific time. Instead of looking at the summary of all the hidden states, which is C in our case. So you're actually telling the model, you're training the model to pay attention to certain specific area, and that's attention. So the probability of the word at yi is dependent on the previous word, the hidden state of decoder, and the hidden state of encoder at that specific time. You want to go back and look at the input source, which is called attention. So you actually are training the model to pay attention to certain portions of input to do a better job on the output.
So is it sequential that the input came in a certain flow and output between the same flow?
The attention is not sequential. Sometimes when you are writing, let's say, a summary of a third line in the summary, but you want to go back and check the 10th line and the first line for doing a better job in summarizing the 5th line in this output, then you go back and check in the first line and the 10th line, which is, and hence not sequential. It's not sequential. It actually goes, so what it does is, if you look into this picture, it's looking at, ignore the right arrows and left arrows for the minute, and I'll explain that in a minute. But let's say this is a LSTM, and you're giving a series of inputs. At every time step, you have H1, that's the hidden states are computed. But you take a variable called alpha t, which is a number between 0 and 1 that gets multiplied, and all the outcomes, that is alpha t1 h1 plus alpha t2 or h2, all of these numbers are added up. And if, let's say, while decoding, if you're in the 5th sentence and this 5th sentence says, you know what, I need to look at the 1st sentence and the 3rd sentence, the alpha numbers for those will be high, and the alpha numbers for all other hidden states will be almost zeros. And that's part of the training. How does it do it? That's again a magic too. It's part of the training, how you train the model, but it knows, because you actually have, when you're training the model, you have the source information, and then you have the ground truth where you're actually training the model. So the model figures out over a period of time, when I do the 5th sentence, I got to go back and check in the 1st and 5th line, or 2nd and 7th line, whatever it is, it figures out.
Is that block repeated for every
Yes, yes.
Is that lower?
It does the math. It does the math all the time. Yes.
Sounds computational.
It is. It is actually talking about just. I'll come to in a minute. I thought I'll mention that towards the end of the presentation. I'll be actually presenting in a different meetup on image processing. there's a lot more exciting activities happening in image processing. Of course, this is text processing we're talking about now. Let's say if Amazon right now, if you go to Amazon and give a search, you type in the word what you're looking for, and it gives you the hits. But what if you have seen something and you want to give that image to Amazon, and it figures out what you're looking for? So that's in the whole of retail industry, or similarly in the healthcare industry also. You have a scan of your body or a tumor, and then you give it to the doctor. Doctor sometimes gives it to the model to figure out what the issue is, which will be a second opinion for the doctor himself. So there's so much of exciting activities happening in image processing, and I'll talk about that. In that, the numbers at every time step, it'll be 150 million numbers are being computed at every time step. That's why the training of an image processing model will always runs into multiple weeks, or even not months, but I think days to weeks. Even if you're using the smartest and the toughest hardware, it takes multiple weeks. The reason you want that to happen in the training, it takes more time, because I think when it's testing or in inferring time, it has to be a fraction of a second so that it gives you a quick answer. That's why it really takes a lot of time to train. So just going back to your point about computational intensive, well, yeah, this is nothing compared to the image processing. Yeah, questions? Okay. I talk too much, maybe, I think. So was the attention, and we're going to talk about the attention in a minute, because I'm going to add up all of these building blocks to show how to create a summarization solution. Next is search. Now, this is at least for me, it was a complicated concept, and let me explain that carefully. When you're doing the output for a summarization, you have the first word, and when the model figures out what is the second word, what it's exactly doing is, after the first word is outputted, it looks at the first word, looks at the attention vector based on the encoder, and also looked at the current hidden state of the decoder, and gives a probability distribution for all the words in the vocab. If your decoder vocab has, let's say, 30,000 words or 50,000 words, it gives a probability distribution. Like every word gets a probability. In other words, what it's telling is, okay, the first word is the second word can be any of these 50,000 words, but I think the 566th word is the best because it gives the maximum probability. Whereas the probability for all other words are very, very low. But actually it gives a probability for each and every word. Now, when people looked at the summarization solutions, sometimes the top word which has the best probability may not be the best word you want to pick. So let me explain that point in a different way. When you're doing a language translation, let's say in an NLP, let's say English to French, and then the cat's out on the mat, there's only one way, almost one way of doing that in French, right? It's maybe a little bit slight variation here and there, but there's almost one way of translating that into a French language. But summarization is not that. When you write the summary for a big article, or you write, you all may be writing differently, different words, different sequences. Maybe you highlight some different messages from the article, source article, but still the summarization is valid. So in other words, there is no one single ground truth. So when you do a summarization problem, when you solve a summarization problem, that is the most difficult problem of all the NLP problems, because there's no one single solution. There's no one right way of doing it. Because typically in machine learning or artificial intelligence, you train the model of what the source is and what's the one right answer, and over a period of time the model figures out, oh, that's the right answer. Oh, that's how maybe I should keep that in mind so that I can give a better answer next time. But in summarization, that's not the case. It's always different. Now, I don't know whether I explained this. Yeah, there's a number called rho. How do you measure your summarization was really good? What's the metric for that? What's the expansion for rogue? I forgot. No. Rogue is an accepted industry metric for computing how good your summarization was. And the actual metric, the computation of the metric is, it will compare the number of words the ground truth had and the number of words the machine summarized output had, and the amount of overlap gives an indication of how good the model was. But here is the problem. You could actually have all the right words, but if they're in the wrong sequence, grammatically erroneous, still you'll get a very high rogue factor, rogue score, but it's completely useless, number one. Number two, you may have different words and you may used by different people, and hence the model may be right or wrong, but you actually have multiple ground truths. Because you ask 5 different people, you can have 5 different, maybe even 6 different summaries. That complicates the whole process. So let's go back to building the model. So when you output the first word, and when you're ready to output the second word, and when you give a probability distribution of all the words in the vocab, the greedy search says, pick the one word which gets the best probability and then move on to the third word. And people have found problems in that process, because if you pick one erroneous word, it actually goes in entirely in a different direction. The sentence could be an entirely different sentence. And then people said, oh, why don't we do a full search? That is, you get the first word, you do a probability distribution for the second word alone, and then do a combined probability of the first word and the second word. For, let's say if you have 50,000, then the 1 times 50,000. Then when you come to the third word, check the combined probability of first, second, and third. So 1 times 50,000 times 50,000. And as you go on, the number of computations you do in a full search, it becomes really, really difficult. So typically scientists, what they do when they have these two extremes, pick a middle. And that's what is called beam search. Instead of going for searching for the entire vocab, pick the top K hits. K could be a 3 or a 5 or a 7 or 10, whatever it is you pick. And then if the first word is, you're done with the first word, pick the second word, and the combined probability of the first and second, you get 7 hits, and pick only those 7 hits. When you're going for the third word, the combined probability of first, second, and third, you pick the top 3 or 5, whatever is the K, and then move on. And so you do a beam search on what's the right word. That would help in making it computationally easier, and also I think they are compromising a little bit of a quality in that, but I think people I think are okay with that quality. Random, sorry? Random forest. Actually, when you do them, I don't know the answer. It's not. I don't know whether it's random forest or not. But in the neural network, when you do a softmax on the outputs, it actually gives a beautiful probability distributions for each of the word. It gives when you look at the unnormalized number, it is just a random number, because W X plus B, which is a typical neural network translations, W being a big massive matrix and B being a scalar which adds up, and X being the input, you get a random number. It could be a fraction, or it could be thousands or whatever number. And if you look into all the numbers the words get, 50,000 words, you normalize those numbers and they become a probability numbers now. So it's, I don't think it's not random forest. So with these building blocks, let's start constructing. So the first step you can take summarization is, people have actually used sequence to sequence, and they were giving a decent outputs. Now remember, before the neural network method was used, which is actually called abstraction way of summarization, 5 years ago and before, there was another method of summarization called extraction method. So you actually pick a few words from the source, club them together and create a sentence out of it, and then that's called extractive, where you're actually extracting words from the input, which was not effective in many instances, even though it worked for a long time. But I think when people heard of neural networks, they said, okay, let's go figure out using neural networks, and it starts generating words which were not in the source vocab or the input vocab. So every encoder has a vocab, every decoder has a vocab. The training of the encoder, I think if you have a 50,000 or 80,000 words, I think it's fine. But when you're doing a decoding aspect, decoding, it takes more time even during testing or inferring time if you have a huge vocab. So people, I think, are scary of doing it. So you can do sequence to sequence. Bidirectional sequence to sequence is what I was showing the picture earlier. Sorry, going back. Bidirectional RNN or bidirectional LSTM is nothing else but you stack two neural networks, RNNs or LSTMs. For the first one, give inputs in a sequence, that is x1, x2, x3 to xn or xt. For the second one, give the inputs in the reverse order. So the first, at time step t is equal to 1, you give the last word in the sequence, and then you keep on giving the last word and stuff. The logic behind when you do a bidirectional LSTM is this LSTM at timestamp t1 gets x1 as input, but this one gets xt as inputs. So the logic is sometimes the model needs to know not just what were the previous words, sometimes it needs to know what were the future words. Because sometimes you can actually make more sense, the model can do a better job of summarization if it also knows what the future words are. So having a bidirectional LSTM will actually gives access to those words that's going to come a little later. But the problem with this, let's say if you have a sequence of let's say 10 words or 20 words, the first word and the 20th word comes first, and then the second word and the 19th word comes, and then you concatenate the hidden states of these LSTM at every time step and then use it for attention or use it for any purpose. But it is not the most effective, but it is better than just a unidirectional sequence to sequence. Bidirectional sequence is better. Then people started using encoder and decoder, it starts summarizing too. But it was the problem with the till encoder and decoder in summarization, it was doing an excellent job provided it had 2 or 3 problems. One is they found that the decoder starts repeating the words, sometimes repeating this message or the sentence which it already has outputted. In other words, the first sentence, second sentence, and the third sentence is almost similar to the first sentence because it just forgot that it's already summarized that portion of the input message. So repetition was one. Second was something called OOV, out of vocab words. When you are generating words, you got to create, let's say, if you want to create, don't have an example right now, but you got to use a new word which the model has not seen. In the decoding part, the model wants to think of a different word, but if it's not there in the decoder vocab or the encoder vocab, many times what people do is they'll say, fine, why don't you put an unk there, unknown, U-N-K, but then the summary is not really beautiful. You see a bunch of unks there based upon how efficient the model is. Sometimes people said, okay, if you don't know the right word for summarization and if you know that's the sentence you are focusing on, pick the whole thing and then put it in the summary. But again, it's not really the smart summarization. So that's where the encoder decoder actually had started having problems. Then came a few techniques. You started using attention. Typically, attention is used on the encoder side. People have not used attention on the decoder, but people started using attention on the decoder side too, and hence they found the quality going up, and I'll talk about that. Sometimes you refeed the decoder. Let's say in training, the first word is Y1, and before the model goes to the second word, when it's to create the next word, it's a good idea to input the Y1, but in this case not Y1 but Y1 prime, because in the training you know the ground truth, you know what the right word should have been, even if the model has made a mistake in picking the wrong word as Y1, but when you give an input at timestamp 2, instead of giving Y1 as an input, you give Y1 prime, which is actually the ground truth. So during training, the model is constantly being told, oh, that's not the right word, this is the right word, but anyway, go ahead, give me the second word. And let's say the model makes another mistake on the second word, oh, that's not the right word, but never mind, go to the second word, third word, but this is the second word. But in the inference time, you don't have that luxury because you don't know what the right word was in the first place because you don't know. And hence it's called exposure bias also. During training, you know what the right word was and hence you could do a better job. But when it comes to testing or inference, you don't know that and you don't have the exposure bias and stuff. So people started using decoder attention, refeeding decoder. I'll talk about two major papers. 7:22, I think we have another 10 minutes I think to go. I'll try to. In 2016, actually it's just 8-9 months ago, there was a new paper published where they said instead of using a single encoder, the entire paper summary is this, instead of using a single encoder, use two encoders. And the reason for that is, human beings, when you read an essay and then you try to do summarization, typically you read 2 times. I read 3 times, but let's say people I think read 2 times to do summarization. And I said, okay, why don't we design a neural network model for summarization which actually mimics human behavior. So let me show you a picture of how it does. So this is the LSTM where you're giving the first input and then second and so on. And you have the hidden state, and the first time when the model is the LSTM is being initiated, you don't have a hidden state. So you actually have some random number or sometimes 0 as given as a hidden state. So based on the previous hidden state and the input, it starts creating the new hidden state, and that goes to the at next time step, the new hidden state with the new input, it keeps on. So this is the regular LSTM we already studied. But then they said, okay, we're going to have another encoder which actually takes the hidden state of the first encoder immediately after the first input, but we input the x1 again to the model. So you have the x1 going in and the hidden state h11, the one on the top talks about the first LSTM, and here you see the 2, that's for the second LSTM. So you have the hidden state at time step t1, the input, and also the hidden state at the end of the sentence. So you are feeding your encoder with so much of information. You're talking about the input, you're talking about the previous input, you're talking about the end of sentence hidden states to make sure that it has so much of information about the word, the next word, the entire sentence, so that it can make a better judgment of it. So that's the entire solution of this paper. And if you have multiple sentences, and it also talks about have a hidden state for the entire sequence. Let's say if you have a 1,000-word input text, you have H global, the hidden global for the entire input also being input. Going back, they also, in this paper, they also talk about a pointer. When does the model know that, oh, I know this word, I have this word in my decode vocab, so that means I have my summarization vocab, this word is there, so I don't have to worry. And when does the model know, oops, I don't have this word, I want to create a new word, it's not there in my output vocab, can I go and check in the input vocab, maybe the word is there. So when do you want to generate a word and when do you want to just find a pointer to where to find? So this model actually talks about if you want to pick a word from the input source, it's actually computing the probability of whether picking up the first word or the second word, so P1s and P2 to Pn, they're computing when the word is. So why T minus 1, if it is need to be picked up from the source, it actually computes it using a different equation. Again, mathematics, but the logic is the model constantly at every time step constantly decides, should I generate or should I go and pick the word from the source? This is again the same I talked about. This is a further extension of almost the same logic of pointer generated, but look at the images. Seems to be very complicated, but it's kind of simple. Here you have the encoder, which is a bidirectional encoder. You see a sequence of inputs going in, and at every time step it actually has its own hidden states, and based on all the hidden states it's computing a attention vector which is called context vector, and using this attention vector it's actually trying to make a prediction on what's the word that's going to come next. But what it does is, instead of picking it from the decoder vocab, it also wants to find out, can I look for the word in the encoder vocab and do a combined probability? Maybe there is a good word in the decoder vocab, but there's actually a better word in the encoder vocab, so I want to pick that. So it actually does a probability distribution of all the words in the decoder and all the words in the encoder, does combine those for words which are available in both. It actually adds up. For the word which is missing in it, it just puts different vocab. So now you have a uniform vocab of encoder plus decoder, and for the common words you have the added up probability, and then picks the right word after that. You had a question? When at the end of the day, when you do the translation or the summarization, you're only focused on what the decoder is trying to output. Now, you can have the same vocab, but it becomes computationally expensive if you have a very high vocab for the decoder. Encoder, you can have huge amount of vocab, translate that into vectors, and that's it, you're done. And then you keep on inputting that to the encoder, and it just processes it and then discards whatever information it doesn't want, and then updates its hidden vector, and that's it, you're done. But when you're doing the decoding, it's doing a probability distribution on all the words every time step, and you don't want that to happen. It takes too much time if you actually have a huge vocab. That's why sometimes scientists don't mind, when you do a summarization, you don't mind a few words, rather than having those rarely observed words also part of the vocab. Let's say instead of 50,000, it becomes 70,000 now, and every time step you are using those 20,000 extra words also to do a probability distribution, which is useless. So that's why they don't do that. So in this model again, which is published I think as recent as just a couple of months ago, the rogue factor has been went up for them, and so it took a while for me to look and understand the picture, but if it's the same case, I'll not be surprised. So when I post these slides, you should go back and then have a look at them, and then I know you have questions. I will answer the questions too, but I don't want to be late. So let me finish my talk, and then whenever there's a difficult question, I can run away. No, but just we can hang on to the questions, please. Yeah. This is the last paper I'm talking about. This is actually written by one of the guys, is Richard Socher, and if you guys don't know anything about NLP, and I met him once, and for the first time in my life, I'm not a young guy anymore. First time in my life, I took a selfie with him because he's such a famous guy, and I even told him that you're like a god in NLP world. He's a young chap, I think graduated from Stanford, I think 5-6 years ago, doing PhD, and now he works for Salesforce. But anyway, he's an extremely smart guy. So if you see him next, and if you tell him that I was telling him that he was like a god. So this is one of the best papers I think published again just a couple of months ago. They have used all of these best practices mentioned in the previous slides I mentioned. So they have bidirectional LSTM, they have attention for the decoder, attention for the encoder. They used, what else they used? So you actually see the attention for the encoder is encapsulated in a context vector C, and attention for the decoder encapsulated in blue color C context vector, and H is the current hidden state of the decoder. All of those numbers are used to actually run a probability on the decoder vocab to identify the right word for that. And the best part is they also added another technique to enhance the accuracy, and that's called reinforcement learning. If you've not heard of reinforcement learning, I think it's a good idea to learn. Some neural network activities, you can't train a model on a step-by-step. Let's say you're training a model to play chess, and if you have seen chess being played by international grandmasters, the losing grandmaster is not a stupid guy or a girl. They're very smart too, but the sequence of steps they take, eventually one person wins and one person loses. But if you really want to train a neural network model which which is a winner all the time, you don't know which step was wrong, because every step in that current time is an accurate step. No one actually makes an intentionally erroneous step, right? When you're playing chess. But at the end of the 20 steps or 30 steps or 40 steps, one game is a winning game, one is a losing game. So reinforcement learning is where you give all the sequence of inputs and you have a rewarding policy where you actually reward the model for whether to give a reward or a penalty based on the outcome, not the individual steps. But anyway, I think in the context of summarization, reinforcement learning, what they've done is they create a summary using the model. But how do you know this is the best summary? Sometimes it may not be readable. Sometimes it's not really concise. Sometimes the model highlighted a couple of points which are not really the best top points you want to summarize from the source. So they make the model generate two outcomes, and then they also have the ground truth when they're doing the training. Ground truth plus two outcomes, they train the model and tell which one is a better compared to the other, because they create a vector for the entire summary. It's a reinforcement learning where they give the inputs of these two summarizations created by the model plus the ground truth, and then they form the model. Anyway, that really came out well. This is in 2017. Guys, we are in the month of, what month we are in? September 12th. These are some of the papers, and there's so many political debates going on in the United States and also I think in Europe because of politics. There is a model which actually automatically summarizes online debates and also identifies the topics. So you actually can see the graph of hot topics going up and down, what topics people are talking about. There is a model which will summarize the video discussions using subtitles. So you actually, if you see a movie and you can just want a summary of the whole movie just by looking at the video. And there's another model which actually talks about course to fine-tune headline creation. So this is the actually image where they run the model multiple times until it gets really the right headline. So if you really do want to do a summary of, you're a news reporter, you wrote a 1,000-word article and you want to get really the best, it asks the model 10 times, tell me the one, oh tell me again, oh tell me again, no tell me again really. And then the 10th time it gives you a nice one. That's called course to fine-tune headline creation of the model. So if you want to, yeah, we can talk later too, but anyway, that's my last slide and I'm open for questions. Yeah, go ahead. There are lots of open source data sets available. It's called DUC 2003, DUC 2004, CNN data set and Daily Mail data sets are available. There are lots of data sets available. You can use them, and all the papers being published, you use the same data sets because that's how you can compare with each other. Those can be considered as a gold standard. But in summarization, as I told you earlier, there's no single way of summarizing, so there's not really a gold standard. But they have to pick some gold standard because that's how they can actually train a model. Yeah, there are some gold standards available. These are all open source data sets available.
So, you're talking about healthcare, right? So in healthcare, temporal instances or events, how they occurring are very important. I understand incentives, how you take is very important, but when a particular event happened, after that what happened, after that what happened. So I know how extraction was with rule-based externalization works, but how well does neural network help with that?
Sure. So that question is actually a good question, and I'm actually working on the healthcare solution itself. None of what I spoke in the last one hour works for that. So there are two ways of doing it. One, of course, I can give a quick answer. This one has been deactivated, so I can't use this. The question is, for a healthcare analysis where you have a patient going through multiple tests or visits to the doctor over a period of time, and that's temporal data. How would analyzing that data in the context of the time would be used in the context of what I spoke? And I said, none of this what I spoke I think is going to be useful, but there's a lot of primary analysis of text called parts of speech tagging, tokenizing, chunking, and lemmatizing and summarizing. You actually can do this, and then you identify the subject and the object and the verb and adverb and all of that stuff, and then you write a lot of program to understand for one object what was the dependency and over a period of time. But if you want to really find easy, if you go to my LinkedIn, I did exactly a 4-hour tech workshop on August in a global big data conference. And what I did was I actually video recorded my stuff for 4 hours and 3 videos, an hour and a half on each, and I wrote a blog. It will tell you how to listen to the videos and what from. I've actually answered this question there, so maybe.
So actually, I have spent like 7 months of my life writing that for company where you do ontology and the same words, like what kind of word is used. So it was an extremely tough situation. I just want to know
Yes,
how.
that's the reason why I think there's so many startup companies working in healthcare. And if you want to start a company, healthcare is the best thing, because if you just say healthcare and go to a VC, you get lots of money. I'll give an example. I was talking to a company, and of course, I'm not trying to belittle the problem statement. It's a noble cause, but what they're doing is they're trying to tag patients with the right human trials. I was even worried for a man. You don't need AI for that. You can just do a basic SQL statement and then figure out for all the criteria A, B, C, D, which is the right trial. They got $5 million for the next year and a half. I was thinking, wow, I would like to do something similar too. But anyway, there's lots and lots of money. There's one company I heard in Berkeley which is doing for Alzheimer's patients. So when patients fall down, you can have any of those devices on you, and then it knows when you're falling down. Let's say even an iPhone actually knows when it's falling down. But sometimes in patients, Alzheimer's patients, they're not really falling down. They may even slowly fall down. And the model doesn't know that maybe you're trying to sit down on a chair, but you slip and fall. Or let's say you slowly sit down and fall off, or let's say even sitting on the bed and then fall off. But if you're in a nursing home, someone needs to really come and attend on you. So there are models which are actually video recording the whole stuff, and they know the difference between you sitting down or lying down on a bed versus falling down. And they got lots of money from VCs.
What's the name of
Can't tell you that. Because then I think it's a good. I know the people side. I'm only trying to say that if it's a healthcare problem, AI problem, healthcare, you're sitting in a gold mine. I think you should talk to VC and then get money. Yes, sir.
Is there any analysis of the ratio of summarization to source? Like, is there like a sweet spot that says be no more?
I don't know. You're talking about the rogue factor. Some of the best, I think, rogue factors are around 39, 40, 45%. In other words, 50% of the words which the model created was in the ground truth or in the human summarized thing, which actually is a good thing because you're actually creating sentences, grammatically correct sentence. You're picking the summary part of it, and also you're sometimes generating new words which was not in the source, which is actually the beauty of the neural networks. But bringing the accuracy rate to 100% of it is going to take time. But even the rogue way of measuring itself is wrong, because you're just looking at the words, matching words, and if they are in the wrong sequence, etc., it's gone. So
the quality of the summary depends, it's subjective. How do you evaluate how well the summary is? How good the summary is?
rogue is the score which is being used right now, but readability, the presentation of the summary, sometimes which points in the source you're highlighting in the summary could be different based on each human being. So there is a disagreement on what would be the right way of doing it, but today, if you want to write a paper and if you want to measure how good your model is, rogue is the only way of doing it.
So sometimes when you have input devices like speech to text, different devices can make different types of mistakes. So how sensitive are these models? And then I have a related question. I don't know if it's related. Let's say you have a conversation going on between two people. One is there is measured speaker, and the other is, say, between Alan Greenspan and Jim Taylor. So how do models take the difference into account?
I'm not sure whether the summarization problem. I'm trying to understand what context you're asking the question. But if it's a more of a speech to audio or text translation, you're talking about transcription, and actually that's another problem statement of mine which I'm working on. But I think that's not the question I think you asked. Sorry, yeah.
If you're doing transcription, the inputs can be different, and therefore the summary can sometimes, for example, I was reading a story today where the speaker is talking about use cases. In the transcription,
Sure.
Very different.
Then I think you're talking about, there are two pieces for the problem statement what you just mentioned. The transcription, the accuracy of the transcription itself, that is from the audio to the text. And there's only one ground truth in the process. And the model, depending upon the model, right now I know for 85% in really some models, there's a company called Lingvamatics. Yeah, Lingvamatics, yeah. I think they have a 92% accuracy transcription services. And that's expensive, but yeah, they also have open source tools available at 80% available. But if you're using it for a regulated industry like a healthcare, you can't be having anything less than 100%. So I'm actually, I'm working on this healthcare solution. So I'm working on an approach where there's a concept called language model in NLP. And if you have a transcribed text available, which is let's say 80% accurate, 85% accurate, and you attach a language model to that, language model is nothing, in simple terms, it knows what the next word should be based on the previous set of words. And most open source language models available are trained on Wikipedia. So assuming Wikipedia has a real good distribution of the various topics and grammatically correct English sentences, the model is smart enough to figure out what the next word is. So I'm working on a concept where I can connect a language model to a transcription output and see if I can bring it to 95, 98%, and then give it to the doctor immediately, because doctor still remembers the context. So instead of having one word out of every 10 words being erroneous, but let's say if it's one word out of the 50 words, maybe a less effort for the doctor and less irritating for the doctor to actually solve it. So that's anyway, we can talk offline for the question.
It's striking that directionality is missing in what you say. It's like talking about squared correlation coefficients versus sine correlation coefficients. You at the beginning you pointed out absolutely the cat on the mat on the cat. It's conspicuous that even at the end you have not answered that, and it's so fundamental. Can you speak to that?
Yeah, so the cat sat on the mat, and on the other way, I was talking about it in the context of creating vectors for the words. One-hot vectors and co-occurrence vectors, when you translate a word into vector, they don't capture the sequence, but they are proven to be successful in certain NLP problems.
No,
But
even
if
in your latest stuff, you didn't capture the directionality that seems to be so important in meaning. Again, so important in meaning correlation.
I don't know. Let me understand the question. So the one-hot vectors and co-occurrence vectors don't capture the sequence, the directionality of it, but word-to-vec and GLOW, they capture the sequence and directionality of it. And depending upon what type of vectors you use, they give different results. So many times when people do the scientific and NLP research like summarization or question answering, they use multiple vectors, multiple approaches to create vectors and see which one is giving a better result. So in other words, to summarize, word-to-vec and GLOW sounds logical that because they capture the sequence may give a better results, but in some instances, one-hot vectors actually were giving good results. There's no answer for that why one-hot vector, because I have my personal experience, and if you go to my LinkedIn, actually I have a blog written on, I created a model to train the model on a huge Indian story. It's around a massive story. And then after that, I did question answering on the model, and it was giving 72% accurate answers. But I used one-hot vectors where I took the complete text, removed all the stop words, removed the sequence of the words, arranged them in an alphabetical order, and created a one-hot vector of it, and still it worked. I don't know why. I don't know the reason, but that's part of the unknown in the NLP today. At least I am not smart enough to figure out why. I don't have time to figure out that. Yes.
I think what you might be referring to, you said that the road didn't give you credit, or that it was not a metric.
Yes.
As a metric, it was a bad metric, not necessarily the output.
So you're right. Rogue as a simple metric, I think, is not really serving the purpose, but I think people have come to accept that. But within Rogue, some people, I think in this paper I mentioned, the last paper I mentioned, they're using the recall and precision as metrics on top of the Rogue numbers. I don't know if you guys know what is a recall and what is a precision. It's a false positive, false negative, true negatives, and true positive. It's a combination of those, and see how many were the right words, how many were the wrong words. But that's another suggestions, couple of suggestions I've read, but my knowledge does not go to the fact that what's the right metric at this point. I have not found what would be a most intelligent metric for comparing summarizations, ground truths versus the model created. Yeah.
If you resubmitted the summary into the engine, how many iterations would you have to go through before the summary and results are equal?
Good question. You can keep on going, and I think eventually there's no output. Maybe you just say end of the sentence token, I think comes out, and that's it. You're done. I don't know. Actually, there's a good fun exercise. You have this Google Translator, right, on your phone. Take two phones. You have English to, let's say, French, and then the other one is French to English. Make each of them talk to each other. After some time, it'll be completely gibberish. Yeah, it's the same thing what you said, I think. But in translation, they are supposed to be a very intelligent model. But once you give a first English sentence, it goes to the French, French to English, French. All of these things. After some time, the English sentence you gave and what the model is giving is completely nonsense. But
So you mentioned about finding probability of certain word condition on all the previous words outputted by the decoder. So basically, you're trying to find the joint probability of all the words appearing in sequence. So do you provide any kind of prior to the first word?
no, first word is actually created by the model because you give a start of the sentence token. Many times you actually train the model. The most commonly used is end of the sentence, start of the token will be the word start and the word end. So the
Basically, what I'm trying to get to is you're doing some kind of a joint probability. Basically, you are splitting a joint probability to
for the encoder vocab and then decoder
So,
vocab.
what is the prior probability of the sequence? How do you decide that?
I don't understand what a prior. We can take it offline. I've heard of the word prior, but I'm not really familiar with it.
I was just interested in other extensions or applications of this concept. For instance, if you could take the issue of diagnosing a certain condition and you could take different doctors' assessments of what it is and just feed it into it and see if there was a concurrence or something, and then also to identify where the outliers or different insights might be. You could do the same thing for
Sure.
crime scene analysis or any different thing. I was just curious about
Oh yeah, there is actually a famous story that's going around in the NLP world. In the image processing in the healthcare industry, what they did was they actually picked image scans of tumor, I think scans of cancer patients, of 100 patients, and they picked 17 radiologists, and each radiologist was given the same 100 scans, and each of them will identify which one is cancer, which one is not cancerous. And then they turn around and give the same 100 cases to the model, and then model actually makes a prediction. If you say 17 radiologists, of course, let's say some say yes, it's cancerous, some say it's not cancerous. So you actually have a distribution. Let's say for the first patient, 7 people said yes, and the other people said no. Second patient was 10 people said yes. So all of the distribution, the model consistently predicted better than all of these 17 radiologists in terms of whether the scan is cancerous or not. So there are instances available, but I don't know whether humankind has come to a stage where you will believe a model than a doctor. So right now when the healthcare, so when you start a company in healthcare, don't say that we are going to replace the doctor, then you will not get money. You say we are going to empower the doctor to make the right judgment, and then you'll get the money. I think we're done, yeah. Yeah, thank you guys, thank you very much. Yeah, thank you.